All right, welcome everybody. So 2014 has been a real banner year for Java. We shipped Java SE8 and Java ME8, both of which have been huge leaps forward. Java 8 is the largest upgrade we've ever done to the Java programming model. And unless you've been hiding in a cave for the last few years, you probably already know the big new feature of Java 8 is Lambda Expressions. And there are almost as many talks at DevOps this year about the new Java 8 language and library features as there are time slots in the schedule. So there's lots of opportunities to learn about it here at DevOps. The short summary of what Java 8 is going to do for you is having Lambda expressions in the language enables the creation of more powerful libraries and frameworks, which in turn enables, improves developer productivity and improves the readability of, and performance of Java code. So Java 8 is really cool. It's really exciting to sort of see it in the rearview mirror, having worked on it for 3 or 4 years. But Java 8 is more than just Lambda. There's lots of other new stuff in there. There's a new datetime API. There's the Nashorn JavaScript engine. There's Java FX8 and lots of other good stuff. So amazingly, Java is almost 20 years old. And it's pretty interesting to look back the last 20 years of Java, but we also want to look ahead to the future of Java. And as stewards for the platform, we have to ask ourselves, what do we need to do to ensure Java's relevance for the next 20 years? Now, in my opinion, the best way to do that is to stick to the design principles and values that got us here in the first place. So last year at the Keynote for DevOps, I talked a lot about the forward-looking decisions that were made 20 years ago by James Gosling and his team in the very early days of Java. The choice to use garbage collection and dynamic compilation and dynamic linkage, all of which were risky decisions at the time. And so what I'm going to talk about a little bit today is our approach for evolving the platform since the early days of Java. So the problems that we solve with the programming language and the hardware that we run on all come from the real world. And the real world changes over time. And programming languages need to evolve to meet the changing needs of developers. Otherwise, they risk becoming irrelevant. So rather than trying to guess what the future is going to bring, which is always a risky game, in the evolution of Java, we prefer to take a somewhat more conservative approach and focus on identifying pain points that developers are experiencing now and try to ameliorate those problems rather than imagine what problems that we're going to be solving tomorrow. And this has been a pretty good track record for us. So as we evolve the language, we adopt good ideas from elsewhere, from other languages, from the research community when they've proven their value. And occasionally, we come up with our own stuff as well, but we try not to just throw every random feature idea into the language because that's a recipe for becoming Perl, and we don't want that. 10 years ago at Java 1, Graham Hamilton enumerated some design principles behind the design of the Java language. And we still look to these principles today. The basic principles are readability, simplicity, and transparency. Code should be easy to read, it should be simple, and it should do what it looks like it does. And these are principles that we've gone back to time and time again as we've evolved the Java language. And even in the early days of Java, it was clear that we were going to need to evolve the language and the platform as we went. Again, the goal was not to add as many features as we could, but to add as few as were needed to meet the evolving needs of developers while respecting those core values of readability, simplicity, and transparency. If you happen to have been at the recent Java 1 conference in San Francisco at the community keynote at the end, James Gosling told a very nice little anecdote about why generics weren't included in the 1.0 version of Java. And it was not because the need wasn't understood. It wasn't because the benefits of parametric polymorphism were not understood in 1995. It was known that it was needed. It was that they had not yet found the right way to do it. And sometimes it's better to do nothing than to do the wrong thing. And so, if they had done generics in 1995, we would have gotten something like patterns from Beta or templates from C++. And, we did have to wait a little bit longer, but I think we got something that was a little bit more Java-like. So generics ultimately took, 10 years to add to the Java language, which is longer than anyone would have liked. And certainly by the time it happened, it was very much needed because as time marched on, people were using Java to build bigger and bigger programs, and the limitations of the type system were starting to become more obvious as an impediment to the scale of programs that we wanted to build. So I'll talk just very briefly about generics just in historical context. But like the dirty secret of Java 1.0, for those of you who remember programming in Java 20 years ago, was even though the language was strongly typed, without generics, any non-trivial data structure was effectively dynamically typed. And the immediate result of that was code was less readable, it was less reliable due to, errors at runtime that were sometimes unexpected. And this might have not have been a problem for small programs, and of course, the first programs we wrote with Java were all small. But it became a huge problem as programs grew because you had assumptions buried in the code rather than being explicit in the program interfaces. And the bigger problem that forced us, that motivated us to do generics was the inability to statically type check interactions between classes and modules was a limiting factor for programming, for program scale. There was just only so big a program you could build without having reliable building blocks to build on. So what generics were about was abstraction over types, so that you could have a list of integer and it shared list nest with list of string, and that allowed us to turn what were runtime errors into compile time errors and catch errors earlier. And so that's a good thing, more reliable programs. It's easy to get, especially if you're into programming language design, it's easy to get wrapped up about language features, but language features are not an end unto themselves. They're just a means to an end. And very often when you change the language, you have to change the libraries with it. And this is what we did, in Java 5 when we added generics, is we generified all the libraries along with it. But we also were mindful that we didn't want to force developers to update their code at once. And so we updated the collections in a compatible way so that you can continue using the same code you were using before and get the benefits of better type abstraction. So 10 years later, even if you hate generics, it's probably hard to imagine building a large program in Java without them. So time moves forward, and new problems move to the fore. Just as the inability to abstract over types, was a problem in 2004, the inability to abstract over behavior was becoming a serious problem for Java development, in 2014. And poor old Duke is just struggling to keep up here, right? So, as you all know, the big feature in Java 8 is Lambda Expressions, and Lambda Expressions are about representing behavior as data. Now, we always had a way to represent behavior as data. We could use inner classes. Inner classes were around since, Java 1.1. We could do it, but it was painful. And more important than being painful, it obfuscated what was going on in your program. So if you take this little snippet of code and you replace the inner class with a Lambda expression, not only does the code get more compact, which is nice, and it's easier to type, and that's nice, but the really important thing is it's more transparent. When we convert this code to use a Lambda, it makes it a lot more obvious that what's being passed to this library is behavior. It's not just an object, it's behavior. We're saying, do this when the button gets pressed. So this is clearly a big improvement, but I'll just repeat the point again. Language features like Lambda aren't an end unto themselves. They're enablers. What are they enablers for? They're enablers for better libraries. Well, what are better libraries for? Well, that's an enabler too. Better libraries are enablers for what's really important to us. More readable, maintainable, less error-prone code. So, speaking of better libraries, here's an example that we've probably all seen before at conference presentations using the new streams library that's in Java 8, which takes a collection of person objects and does a filter map reduce query on it where you're saying take the people, select the ones that are male, for each one get their weight, and then find the largest weight. So that's the weight of the heaviest guy. And obviously, Lambdas were a key enabler for being able to write libraries, expressive libraries like streams here. But anybody who's programmed in other languages like JavaScript or Ruby or Python, may very well look at this code and say, oh, big deal. Java's been able to do this. Other languages have been able to do this for years and years, and Java has just caught up, right? And that's true, right? We finally caught up in expressiveness with some other languages, but catching up isn't really good enough. So I want to look a little bit about some of the places where we've leapt ahead of other languages that have had idioms like this for years. So not only do we take this to the next level with integrated parallelism, but we've done an awful lot of work under the hood throughout the JDK to make aggregate operations fast, whether they're sequential or parallel. So there's a lot of detail in this little code example that's sort of floating under the surface. all of the collections implementations in the JDK have been retrofitted. They've been retrofitted to support faster access to elements and support decomposability so that they can be sources for parallel computations. And similarly, these stream operations, filter, map, reduce, they all work off a general abstraction for accessing the data, which means not only our collections, but your collections or any other data source, like a generator function or an I/O channel or a query, can be used as a source for a stream pipeline. And if you look at this code, it may look like it's actually doing three separate operations. First filter the data, then transform the data, then reduce over the data. But in fact, the implementation uses laziness under the hood to fuse them into a single pass on the data. So this is going to be a single sequential pass or a single parallel pass on the data to get your answer. So it's actually really fast. In fact, it may be faster than the corresponding for loop expression. So not only have we caught up with some other languages in the expressiveness department, I think we really blow them away in the performance department. So you're probably tired of seeing that example because we've been trotting it out at conferences for years. And it sort of seems like a little bit of a cheap example because realistically the imperative version of like find the way to the heaviest guy, that code's not so bad either. But the real problem is the imperative approach just doesn't scale. So this is some typical idiomatic Java code that does a query on a collection, and what's immediately obvious from this code is it's not immediately obvious what's going on. And the reason for that is there's just a lot of accidental detail in this code, which means to see what it does, you've got to wade through the whole thing line by line, and it's easy to get it wrong. So what this code does is takes a set of transactions, picks out the ones where the buyer is over 65, finds the corresponding sellers, sorts them by name, and print them. So if we recast this code using the streams framework, this immediately brings the essence of the calculation to the fore, and the code reads a lot like the problem statement. Take the transactions, select the ones where the buyers are over 65, get the sellers, throw away the duplicates, sort them by seller name, and then print them out. So when code reads like the problem statement, it's more likely to be right because you can immediately look at it and tell what it does. Okay, so let me talk just a little bit about the other big new feature in Java 8, which is default methods. This one was less obvious than Lambdas. It was aimed at a problem that new languages don't have, which is evolving existing APIs. Most of our APIs are defined with interfaces, which are great, but they're also a double-edged sword because once an interface is published, you can't add new methods without breaking existing implementations. But if we didn't evolve collections to work with Lambdas, that would have really been terrible. And we wouldn't have been able to do all the cool stream stuff I just showed you. And people would not have wanted to switch to a new data structure just to get the new features. So evolution needs to be compatible because we can't go and break your code or demand that you switch to a new library because people aren't going to do that. So the solution turned out to be fairly simple. Default methods, which let you compatibly evolve an existing API by adding new methods and adding a default implementation or a fallback implementation. And default methods are just like any other interface method in the sense that they're virtual methods. From the outside, the caller can't even tell whether it's calling a default method or a regular abstract interface method because they're just interface methods from the outside. Sort of as a bonus, even though our primary goal for adding default methods was interface evolution, they're useful in a lot of other ways as well. And people have sort of figured out that they're almost sort of like traits minus, which was not necessarily the primary design goal, but is kind of a nice bonus. Okay, so let's look a little bit ahead to the future. I hear you asking, well, Java 8's great, but what are you going to do next? Are you guys done? You're just going to put your feet up on the table and relax? So we'll gaze into the crystal ball a little bit. Let's look at a few other places where Java developers have to contend with pain points. Java doesn't scale as well as we'd like down to small enough devices. The compact profiles we did in 8 helps, but not really enough. It's challenging to maintain platform security because the internal security mechanism we have is brittle and error prone. It's tricky to evolve the platform because developers insist on using internal APIs even though we tell them not to. And it means it's hard to take those away. Peak performance is good, but startup performance isn't great. And jar files on the class path only get you so far. They don't scale up so well to large systems either in maintainability or performance. So our solution for these problems is the Jigsaw module system. There's going to be a talk on this at 2 o'clock today by Paul Santos. The goal here is simply to define a standard module system for the Java platform, and we're going to use that to modularize both the platform itself and Java applications, both SE and EE applications. We've decomposed the JDK into a number of finer-grained modules. This is the module graph. And then once you modularize the platform, and that application can just say, here are the modules I depend on, and modules define secure boundaries between components in a way that's easily enforced and validated. And modules encapsulate their internal APIs, which prevents details from leaking out. Enables improved performance, such as fast class lookup time and ahead-of-time compilation. It's going to make the JDK easier to build and maintain. It's going to make applications easier to build and maintain and simpler to deploy. Now, this isn't a feature that's like Lambda in that it's going to change the way you code every day, but it's more of a feature for deployers to make Java applications easier to develop and deploy, and it's going to have a big effect on performance and productivity, even if it's not a day-to-day coding sort of thing. Now, this is also one of those things where to get some gain, there's a little bit of pain. And so we're hoping that developers will sort of start getting ready for Java 9 early. The biggest pain point is now we're finally going to be hiding some of the internal APIs, and applications that use them, despite having been warned many times, are finally going to have to make some changes. And we're already working on creating supported APIs for a lot of the commonly used internal APIs, but we're not going to be able to do that for everything. We're also changing the internal structure of the JRE. In particular, rt.jar and tools.jar are going away. They're being replaced with a more efficient file format. Great for performance, again, but tools that have been relying on them are going to have to change. And this won't affect most libraries and applications, but it will affect tools and IDEs, and we're working with tools and IDE vendors to make sure that that's painless. We know these changes are going to break some existing code. We've already started pushing out early access builds. The builds available today already have rt.jar and tools.jar gone. The removal of internal APIs should happen early next year. And there'll be more on this in Paul's talk at 2 o'clock. Okay, so let's keep looking into the future. Let's take a sneak peek of where we're going after 9. And I'm going to have a talk at 4:40 today, a sneak peek Java Futures talk that's going to go into much more detail. Basically, over the last 20 years, the hardware that we execute on has changed dramatically. So it makes sense that a lot of the decisions that were made 20 years ago are less of a fit for today's hardware. And just as the platform has to evolve to meet the changing problems that we're solving, it needs to evolve to change to respond to the changing hardware we're running on. So Java's basic data model is really simple. You've got primitives, you've got arrays, and you've got objects. And this is nice and flexible. You can pretty much model everything with that, but the way things end up getting laid out in memory may not be ideal for today's hardware. So 20 years ago, a memory fetch and an arithmetic operation cost about the same. Today, if you cache miss on a memory fetch, that's going to cost you 300 clock cycles, which may cost you over 1,000 instruction issue slots. So taking a cache miss is a much more expensive thing than it was 20 years ago. So let's take a look at how Java lays things out in memory, and you'll see why this is a problem. Supposing we have an array of XY points. Okay, so we have an array, the array has a header, and every element of the array is an object that also has an object header and has some data. And if you sort of look at where the memory is going, for every 2 words of memory here of data, X and Y, we have 2 words of object header plus a pointer, right? So that's 3 words of overhead for 2 words of data. That's already getting expensive. If you're trying to deploy on high density cloud platform, you're spending a lot of memory on this sort of stuff. And more importantly, there's a lot of risk that you're going to take a cache miss every time you go to access this data. Now, maybe this is fine. A lot of applications, the performance is just fine. You're not working with enormous data sets. You're not working in very tight memory. But sometimes it's not fine. Sometimes you care about performance. And when developers are unsatisfied with performance, they often do horrible things to their code, right? So they might be tempted to do something like this, where they cruft up their code by ripping the points into 2 arrays, X and Y, to get better locality. And, all right, this may be a little bit faster sometimes, but what a horrible way to program, right? We don't want to program like this. You lose encapsulation. The code's harder to write. It's harder to read. It's harder to maintain. The underlying problem here that puts us in this situation is that objects are really too general, and the primitives that we have are really too rigid. What we'd like to be able to do is define aggregates that behave like primitives, but support better abstraction. And this is the key idea behind value types, which are aggregates that behave like values. You can pass them by value. You can pass them in registers. You can pass them on the stack. You can pack them into arrays, and you get better locality and lower footprint. So if we recast our point class as a value class, when you pack them into an array, you get the data packed XY, 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 right? So this is a more flexible way to interact with the way data is laid out in memory, and which is more friendly to today's hardware. So value types is one of the key features that we're exploring in OpenJDK Project Valhalla. And the key goal here is to identify those places where users end up being forced to choose between good things like abstraction and type safety and performance. And we don't want to put developers in that situation. We want to give you abstraction and type safety and performance. And so, we need, 20 years later, we need to make some upgrades to the VM to do that, and that's fine. Some related features, in addition to value types, are specialized generics. All the same reasons why you don't like the layout of that array, you don't like the layout of array list. If you have an array list of you want an array list of ints, not an array list of boxed integers. You want your array list of int to have a real int array behind it, and that's what specialized generics are about. And a related project that's going on in OpenJDK is Project Panama, which is about metadata-driven access to native code and data. So basically faster JNI, faster access to off-heap data, and a safe mechanism to tie all these data access together. So these projects are all going on in OpenJDK. It's pretty exciting stuff. This is all for beyond 9, so deeper into the future, but the work has already started, and we're pretty well on our way. So with that, I'll just point us at a few more talks at Devoxx about Java Futures. So today we have the Jigsaw talk at 2 and the Java Futures sneak peek talk at 4:40. And then tomorrow we're going to do a panel, sort of Ask the Experts panel, where you can ask all your hard questions about why did we do things the way we did them in 8, and what are we doing past 8, and all of that. And with that, I'm going to hand it over to Rich and Jasper.